Okay, so let's talk about error detection and correction. This magic of how do I detect when bit errors happen and how do I correct them? At a very high level, and this is a flow chart that describes how this algorithm works. We can imagine, or this is the sending side, this is the receiving side. All right. So imagine we have a datagram that then becomes our data, and the data has D bits. All right. So we've got D bits of data that we're going to send across. That's the actual data we care about. Error detection works by appending or prepending some additional bits of data which kind of represent something about that data. We're going to call this the EDC bits, the error detection correction bits. We're going to append that, and now our datagram, or rather our frame, is this whole piece, at least. So we're going to send across D and EDC across this link that is bit error prone. All right, so when we receive the frame at the other end, the receiver, it's going to receive essentially these two fields, D prime and EDC prime, where D prime may be equal to D and EDC prime may be equal to EDC. But we're not sure because any of those bits could have been corrupted. Hopefully, the algorithm is going to say, are all the bits in D prime okay using the algorithm that we defined to create EDC from D. You can imagine we have some algorithm to compute EDC based on D. We compute EDC prime based on D prime. And if that still is true, if the algorithm still produces the correct results, then we expect that we've correctly sent the packet.
So the algorithm computes EDC based on D, or vice versa?
What you said. It's going to compute EDC based on D. I think this will make more sense when we talk about it in the next slide in terms of parity, which is an actual algorithm to do it. But so the main idea is we add a bit or two or four or however much we want to of this sort of redundant information that protects the data. When we receive it on the other end, if the algorithm, the protection data kind of doesn't match the data anymore, then we know that something's been messed up. And it could have been the data, or it might have been the error detection bits. But we know that it's definitely something's wrong, so we would probably ask for a retransmission if we can't correct it ourselves. So notice that error detection is not 100% reliable, because it may be that we change D and EDC in such a way that it still passes the test. It still looks okay. Error detection algorithms are designed so that this rarely happens. And the more bits we use, the more protection we get. The more bits we use in EDC, the more protection we get.
So it's rare but possible.
What's that?
It's rare but possible.
Right. All right, so let's talk about parity. I think we mentioned this in this class before, or maybe in other classes you heard about it. We can imagine a parity bit is a single bit that's added on to some data. And it represents, it can be either way, but let's say it represents whether the number is even or odd. Okay, we could say this differently and say we have even parity, and that means we will always have an even number of ones in everything we transmit. So let's see what this, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let me change this around. So we're going to say we always, in this example, always have to have odd parity. Sorry, I didn't know which one we had. All right, so we always have to have an odd number of ones. Yeah? So that means that the parity bit, you can imagine we don't know what the parity bit's going to be until we add up the number of ones. Since we have odd parity, that's our scheme. We have to know that ahead of time. We define it everywhere. We're going to add a 0. If we had an even number of ones, the parity bit would be 1 to make it odd. Yeah? So you see how this data is redundant. but it offers protection, right? Only if the number of ones is the correct evenness or oddness can we make sure that do we know that we've got the right data? So you can imagine if we send this data, right? We send this packet and we receive 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0. So that's the error. I tried to copy all these just the same. Like that's the last bit of data, 0. So this is our this is D prime and this is EDC prime. So I think all this is the same except I flipped that last one of the data to be a 0. So this is what the receiver sees. The receiver, because it knows this protocol uses an odd parity, can easily detect, hey, you've got an even number of, right? You've got an even number of ones. Something is out of whack on this. Does it know what is wrong? There's no way it can know what's wrong. We know because we saw it on the other side. What would happen if we flip this one as well?
That would be correct.
So now it appears to be correct, but we know it's not. So this is what we said, it would be rare but possible for an incorrect data to pass the check and say it is correct.
Wait, so is this an algorithm that we were talking about on the previous slide?
Right, this is one algorithm, one way of doing that.
That's really simple. I thought it was like some complex thing.
Well, it'll get more complex.
Well, I know that, but I mean, just even then, I thought it'd be like something big.
No, this is a big deal, and there's a lot of mathy kinds of complex algorithms to do this, and we'll get to some more of these. Here's another way of doing parity. You can actually do two-dimensional parity and have a lot more protection. Oh, notice what kind of bit errors are you protected from with parity?
Single?
It'll definitely detect single bit errors. And it's actually a little bit stronger than that, isn't it? It would also detect if you messed up 3 or 5, any odd number. Yeah. But it will miss every even number of bit errors. Right. Okay. Take a look at this, and let's see if this makes sense. I think this is actually pretty simple if we understand parity. The idea is we're going to arrange the bits of our data into a grid, into rows and columns. And we're going to have a parity bit for every row and a parity bit for every column. Yeah? So this is odd parity again. So the 1, 1. So our data is just that. Yep, just those. So 1, 1, 1 makes it odd, right? That's his. This makes sense, doesn't it?
Where did he get all
That's
these parity
even.
bits from?
That's even. That's even. 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 That should be 0. Because all the rest of them are even parity. That's the author's bad.
But no, where did it get all these parity bits?
We made them up. So the algorithm on the sending side has to be able to examine the actual data and then add all this additional data, in our case parity bits. And you see we've also got a parity bit here that is the parity for the parity bits. Yeah?
So the algorithm creates additional parity bits.
Exactly. Remember I said you're really creating redundant information. You're adding extra information on so that you can protect it. It's really providing this protection in sending the data. Does that? All right. So that's how this is just another way of doing this, which is generally adding some bits on, and then you get more bits over here, and you should be able to kind of reverse the algorithm or kind of run the algorithm again to see if the bits in D prime are okay. Does that answer your question? You want to ask it a different way?
Gotcha.
So the cool thing about this double parity, the two-dimensional parity, is on the receiving side, if it receives this, you can see that we can actually detect and correct the bit that's wrong, because we can see that, right, this is a 1 and it should be a 1. This is a 0, but it should be a 1. This is a 1. It should be a 0. This one, I think this is because of the error that's in the book. That's a 1, 0, 1, 0. I think they messed that up. If we're right, what it would say is, you see how the lines make it very clear. One of the row parity bits is going to be wrong, and one of the column parity bits is wrong. And where they intersect, that is the wrong bit. So we've identified where it is, and we know we can fix it by just flipping that 0 to a 1. Does that make sense? How if you put enough redundant information in, you can not only detect it, but you can correct it. But you see what we've had to do. We had to send 3 plus 1, 2, 3, 4, 5, 3 plus 5 plus 1, 8 extra bits in order to send, what is that, 15 bits. Does that make sense? We had to send 15 plus 8, 23 bits in order to send 15 bits. So that's going to lower our bandwidth, our effective bandwidth, just because of the protocol. Yeah? All right, here's another algorithm for doing error detection. It's one they're already familiar with because we've seen it in the previous chapters. The internet checksum. You remember this algorithm where this is what TCP, what UDP, what IP use. They treat the whole contents of a segment as a sequence of 16-bit integers, and then add them all up. Right? This is the internet checksum. After we add them all up, we do the ones complement. We flip all the bits, and we put that as the checksum. The receiving side, it adds all the bits together, the whole packet together as a sequence of 16-bit numbers, and it should end up to be 0 because of the way this is computed. Remember we said that kind of trick to how it worked? Because this is kind of the negative. What we've done is kind of the negative of all the sum of everything else. So this is another way of appending a little bit of extra data to get some protection. This isn't, I think, particularly strong, but it's okay. It certainly doesn't allow us to correct any errors, but it's just a detection. Questions on the stuff up to this point? Okay, so this is our last example of an algorithm for doing error detection. And this is kind of the most powerful and the most complicated, which makes sense as they would go together. It's based on modulo 2 arithmetic, so that means we only have zeros and ones. This is a very simplified version of arithmetic. It turns out in modulo 2 arithmetic, addition, subtraction, and XOR are all the same operation, exclusive OR. We can do addition or subtraction with XOR. Okay, it's this very simplified version of math, or of arithmetic. What we're going to do is as follows. We're going to see the data bits, the D data bits, as a binary number. Okay? So kind of down here we've got D bits to be sent. We're going to look at those as a binary number. We're going to choose ahead of time a bit pattern that we're going to call a generator, G. It's going to be R plus 1 bits long. And this is kind of magical. These generators are these special numbers that create codes that offer good protection of the data. What we're going to do next is we are going to find an R-bit cyclic redundancy check. So it's a number, a set of zeros and ones, a series of zeros and ones that we're going to call R. And that R is called R because it's the remainder. What that means is that if we put D and R together and make that one long binary number, we kind of append those two numbers together, DR, we make them one number, that we want to find that R such that it's exactly divisible by G in this arithmetic, modulo 2 arithmetic. So the receiver knows, based on this protocol, because of the definition of the protocol, that G, the generator, which is known to both the sender and the receiver, it knows that G evenly divides this quantity DR.
So you're saying D append R.
Right.
Okay.
D appended, or
R appended to D.
R appended to D. We're looking at it as if that's one big number. And if you divide that big number by G, you get a remainder of 0, because that means it's evenly divisible. You follow me?
Mm-hmm.
So that part's kind of, that makes sense. So if you get a remainder after doing that division, and that remainder is non-zero, then there's something wrong. There was an error in the transmission. So the mathematical formula for that is essentially we're going to take D, we're going to move it over R bits. That is, move it over to the left. How do you move something over to the bit? Move it over that many bits? You multiply it by 2 to the R. In the same way, if you had some number 375 and you needed 3 more spaces here, so imagine this is D and this is R. So D is D bits long. So in this case, little d is 3, little r is 3. If we need to move this over 3 spaces, how do we do that? Basically, how do we mathematically append those two things? In base 10, we'd say, well, just take it times 10 to the third.
Times 2 to the third.
Right, so if we're in binary, we take it times 2 to the r. So that'll move it over. And then, so that would make it 375. Let's imagine that D is, 123. So we're trying to append 375 and 123 together. So we get a number that looks like 375, 123. Yeah? How do we do that? Well, we multiply by 10 to the third, and then we add D. Do you remember, like we said, though, addition is the same as XOR. So we can substitute XOR there. All right, so this is what we're going to send. We're going to send this quantity, D times 2 to the R, XOR R. So on the sending side, it has to kind of reverse compute this to make sure that it finds the value of R that will make this thing evenly divisible by G. All right, and to do that, we have to do some long division. You remember long division? It was not fun in 5th grade, and it's not fun now. So we want to find D times 2 to the R XOR R. And we want that quantity to be evenly divisible by G. So that what that's saying is G times some number n, where n is an integer, is equal to this quantity. That make sense? So we can then manipulate the equation. We can bring the XOR to this side, the XOR R, And then we can take it one step further and say, what's the remainder? The remainder is d times 2 to the r over g. So if we do that math, d times 2 to the r divided by g, we'll end up with the remainder. And those are the bits that we need to add on. So that's what this long division represents. If we start, all right, so this is G. We have this 4-bit generator, 1001. We have this data, 1, 2, 3, 4, 5, 6, 6-bit data. Yeah? What's the step? Well, first we have to multiply times 2 to the r, the little r. Little r is 1 less than the generator. So that's 3 in this case, since the generator is 4 things long. So that's why we add the 3 zeros. And then we do long division, where something goes into something else if it's the same number of bits. So 1001 goes into 1011 one time. Okay, so we bring that down, and we do, like in normal long division, we would do subtraction, but it's XOR. So that's 1 XOR 1 is 0, 1 XOR 0 is 1, and then both of these are going to be zeros, right? 0 XOR 0 is 0, and 1 XOR 1 is 0. Okay, so then we see the generator does not go into 101 because a 4-bit number in this arithmetic is always bigger than a 3-bit number. So that's why I put a 0 here. All right. Next, we know it's going to fit once we bring down the next bit, which is this 0 here. Bring it down. We brought down the 1 here, and that 3-bit number wasn't big enough. So then we bring down the 0, so we get this 1011. That goes into it once. Bring it down. Do XOR again. We get 110. So we have to add another, put it into another 0 times. Bring down the next 0 here. Then it'll go in once. 1001. XOR that 1. So 0 XOR 1 is, sorry, 1, 0 XOR 0, 0, 1 XOR 0 is 1. Bring the 0 down one more time to get, which now this 101 goes into this once. And finally at this step we get this 0, 1, 1, and that's what we were looking for this whole time. So after doing this long division, modulo 2, this 0, 1, 1 are the 3 bits that are R. That is R, that is R. So what we would then send is what the data bits are, which is 1, 0, 1, 1, 1, 0. You see those D? And then, so this is D, and then this is R, and R is 0, 1, 1. So this is what we would send in the data packet. We took very great care to create this value of R, create this whole number so that it would definitely be divisible by G, the 1001. Because we did this, if we divide this whole thing, we divide the DR, this means they're appended to each other. If we divide that by G, what will we get back as a result? 0. Right? As long as we actually get D and R, both sides know G to begin with. It's like pre-knowledge. They'll get 0. If it's not 0, it's wrong. Okay. Why do we go through this much of a hassle to compute this stuff?
Because we want to be reliable.
Right. These CRCs have some really nice reliability properties. And one of the nicest is that this can detect burst errors less than R+1 bits. A burst error means it's not just a random bit here and there, but what if 4 bits in a row are wrong? Okay, so this has the property that as long as that burst, that sequence of bits that are wrong, are less than 1 more bit than the remainder, that math will not work out right, and it will not be 0, and we'll detect it. So you see what a strong property that is as compared to parity. So this is why you also see how much work this is. Yeah, that you've got to do this long division, and this is a really simple example. Like the real generators that are used are a lot longer. Like you can imagine a 23-bit generator. So CRC is a lot more computationally intensive to compute, and that's why most of this is implemented in hardware. So there's specialized hardware that does this, super fast, and that's built into your NIC. Questions on CRC? I know it's pretty ugly. Okay, so we might say there is this epic battle between checksum and CRC. Why do we have a checksum? Why don't we have a checksum at the transport layer? And this kind of goes back to what I was just saying. And why do we use, since CRC is so much better, why not just use CRC everywhere? Thoughts? The answer is because CRC is really computationally intensive. The transport layer is implemented in software, and it would be too high a price to pay, perhaps, to require the software to always do this computationally intensive task. Whereas the network layer can make hardware that does the link layer is going to do this in hardware, and that will be much faster because there's hardware to do it. Checksum is very simple and therefore can be done in software. All right. Are we done? Questions?
Yeah. No question.